let's go back to the regularity. Remember, I had put. Um, so let us try to show. So for k equal to 1, yeah, the last W1p for p greater than n, and let us try to show that this norm is less than equal to L1 norm. The first part. If I take p equal to 1, what do I want to show? Is going to be n minus 1, which is less than equal to L1 norm. That is the inequality which I have written. So I was just saying that we will show for k equal to 1 and p also equal to 1 over here. For k equal to 1 and p equal to 1. That's what I'm just taking a particular case. So here what are you showing? As I have said, 1 of omega is contained in L1 of omega, right? No. L2 n upon yeah, n upon n minus 1 of omega. That is what you are showing. Okay? So if I write, this is one of the inequality which I have written before. So here, so this is W11, the first derivative belongs to L1, right? And if you look at it in terms of functionals, what you are showing is that this particular functional is bounded. You remember, if you from your functional analysis, if you have p from n1 to n2, it is a bounded linear map, right? Norm of p of x is less than equal to c times norm of x, right? So that is your usual definition of bounded linear functionals between two Banach spaces. So here we are having Banach spaces. The T is not visible because it is just the inclusion map, identity map from W11 omega into that L n by n minus 1 omega space. So what I'm saying is that it is contained, not only that, this particular map, inclusion map, is a bounded linear map between the Banach spaces. Okay, that is what, when we write this kind of inequality, that is what it shows. And this can be proved. The proof is you can is straightforward. It's not difficult. So instead of working with arbitrary u in W11 omega, we can consider C infinity function with compact support if we are showing for W011 omega, or C infinity functions if we are just showing W11 omega. Okay, so we just use density argument. So use suffice. C infinity functions with or if you're looking at W1 or KP0, then you just take infinity functions with compact support. Once you take smooth functions, this derivative becomes usual derivative. So you can directly work with it. Your functions are integrable, your derivative is usual derivative, and then you can just play around with derivatives and the smooth function and get the required result. Okay. So what do we have here? Yeah, you use your fundamental theorem. What do we have? This is going to be suppose take minus infinity to, you can take infinity functions with compact support. To take from minus infinity to xi, is or the function vanishes at on the boundary. Okay, I'm just doing it in one variable. This is function of n variable. I'm just using the fundamental theorem of integral calculus in the ith variable. That's all. So if I take mod of ux, this is less than equal to minus infinity to xi mod of di dy. Right? In fact, this is what, see here, what do we want to do? We want to find a relation between u and derivative of u. So this is one of the ways we have relation between u and derivative of u. So we just take absolute value, we get this. So here, if we multiply, because we want to take product of, we want to get all derivatives, I goes from 1 to n. Okay? So I take, multiply this with d1, d2, dn. So here you will have mod x power n, okay, is less than equal to all this product power n. Yes, I'm just multiplying, and these are non-negative quantities. So if you do that, right? Sorry, it is just yeah, it is a less than b, a less than c, so a square is less than b into c. That's all I have done. So here ux power n is less than equal to this product. Now what is the p over here? P over here is this, right? I already have n, so I will divide by n minus 1. I want this norm is integral of mod u n upon n minus 1 times n minus 1 upon n, right? So I already got n, I will divide it by n minus 1. So if I divide it by n minus 1, n minus 1. So now we'll see how we can simplify this, because this is individual derivative, right? We want gradient, we want norm of gradient of u. Okay? So we need to combine this individual derivative. Of course, we want norm on this side. So if we take integral over omega and you take integral over this side, then we will try to estimate it. So this particular here, this is integral of x dx. This is xi over here, and this is your dx. Okay, here this is your x variable. This is your x variable. Your functions are these integrals over here, right? So these are individual functions, and these are product of n functions. Okay, so you can think of it as f1 to fn, product of n functions, and I'm taking integral with respect to dx. What I can do is I can apply the Holder's inequality and separate it. That is the next step. So let me just yeah, it's a small. So what do we have?
You see?
Yes. So what do you do next? So I said apply Holder's to n functions, right? So what power do you apply? See, so usually you have 1 upon p plus 1 upon q is equal to 1. Okay, there are n functions. So you will have, so there will be p1, p2, pn. What should you apply so that you will get the correct one? I basically want something that will get rid of n minus 1. Okay. So here you have f1, f2, and these are n functions. So I will have here that is what I want. And observe here each of these I'm saying product power 1 upon n minus 1, right? So this is nothing but this particular function. So let me call it as f1. If I just refer to this integral as fi, then what is it going to be? It is going to be f1 power, f2 power, fn power, right? And so ideally I want to take p equal to n minus 1, right? So if I take n of these as n minus 1, what happens? I will have what will you get? Is it going to be less than 1? No. Yeah, that is bigger than 1, no? So how will you take care of this? How do you take care of this? That's what I'm asking you. It is like I want to get derivative over here. Okay, I want to get derivative over here. Now what should I do? Of course, I can apply Holder's inequality, but if I apply Holder's inequality, I'm not getting n with n minus 1 is not helping me. What is missing? So there is a way to deal with it, because if you directly do like this, it is kind of like even if you see in the notes, you would just wonder how to deal with this kind of situation. So here what I know is that I can separate it out. This is my situation. But if I take t equal to n minus 1, it is not going to help, because I am not getting n upon n minus 1 that is bigger than 1. Okay? But what we can do is the following. If you see 1 upon n minus 1 plus, if I look at this particular equation, what do I get? 1 upon q is 1 minus, what is this?
N minus 2 upon
It should be other way around. It should be other way around. Yeah. Instead of that, 1 upon n. 1 upon n plus this. So what do you get? 1 upon q is equal to 1 minus. This is going to be equal to n minus 1 upon n. So q is n minus 1 upon n. So what I can do is I can think of all these n functions plus 1 constant. I can think of 1 as constant and apply Holder's inequality. Okay. So this n upon n minus 1 gets split in first n functions, and that remaining, that q 1 upon n gets split in that other one. Okay. I can think of like two separate functions. Okay, product of one more. Okay, and I can still do it. So then you will get immediately each of this is less than equal to. So that is why you get your constant c. So this is less than equal to c times each of these fi. What is the power? What is the power? It is going to be, so n minus 1 upon n, power 1 upon n minus 1, right? That is going to be your, that is going to be over your, is it?
n of n minus 1.
Yeah.
N upon n minus 1.
So you have to do it individually. Write it down, write it down. Do it individually. See? Do it individually. Suppose we are having only so you're having a product of these functions di of ui, di of u, di of u, and the product of this is raised to 1 upon n minus 1. Okay, then, and these are n functions. Yeah, but I think it's easier. New pen. If I take this whole function as a whole, then I will put it as I think that's it's easier. So what do you have over here? So this implies mod ux power n is less than equal to integral minus infinity to xi di of u y dy. So this is product I goes from 1 to n. What I will do is I will integrate with respect to dx. Yeah, we want n upon n minus 1, right? Right. So I will have this power 1 upon n minus 1 dx. Okay. So this is over omega. Now if you look at, you don't split it up. I will take t equal to n minus 1, what else that was correct, 1 upon n minus 1 plus 1 upon q is equal to 1. So what do you get? 1 upon q is 1 minus
2
n minus 1, which is n minus 2 upon n minus 1. So what I will do is I will apply to this product and 1. I will not split up. Okay. So what do you have? Therefore, integral of product I goes from 1 to n, integral from minus infinity to xi mod diu dy. This product raised to 1 upon n minus 1 dx. Right? This is my term. So this is less than equal to c times. So here this goes away. We will have integral of omega product I goes from 1 to n, integral from minus infinity to xi di of u dy. Right? Now n minus 1 has gone away. Right? n minus 1 has gone away. And you are left with 1 upon n minus 1. Right? And now you use the geometric mean, arithmetic mean inequality. Okay, so here what you will see is that you have dx over here, okay, and this product you can combine it. Okay. Your xi is going to vary over entire xi is varying over entire omega. Your x is varying over entire omega. So basically, your xi is varying from, say, even if you put it from minus infinity to infinity, your where the values will be taken will be as long as x is inside omega, right? But you are basically having xi varying from minus infinity to infinity. You don't care what happens outside omega. So here, each of these single partial derivative is going to be less than individual norms of your gradient vector. What is you can use your sum norm, right?
Yes.
Norm of a vector is, you can write it as equal to, or it is equivalent to, it is less than equal to sum of the vectors, and also it is greater than sum of the vectors. So individual sum is going to be less than the total sum. So that is what I am going to use. So this is going to be less than equal to c times product I goes from 1 to n. Okay, you can still take it as I goes from 1 to n minus infinity to infinity. Or you estimate it over here. Only thing is your I counting will go away. You can use let me give the product. You will have more. N minus 1. Let me write it like this for sake of simplicity. Then you will know. And now this is product of n terms. Okay. So you can apply your arithmetic mean, geometric mean inequality, and you will get less than equal to c by n. And this is not, square root of 1 by n is not there. So I am going to put here or di of u I goes from 1 to n. So this is based on summation I goes from 1 to n di of u dx and over omega, and you will have this is n upon n minus 1. So if you take it to the left hand side, you will get your L1 norm on the right hand side.
It's coffee time.
Huh? Yeah. They have come?
They sort of do.
Yeah. product of I, and that can be converted into summation. So that n will appear over here. So then later on you will get this is n minus 1 upon n is less than equal to n1. Do you want immediate thoughts or will you say it? It is, but and next time when we go and stand, it's quite hot, yeah.
It's not compulsory to stand there.
Hello. क्या हुआ? हाँ बाहर है.
Mm-hmm.